Okay, so hello, welcome, welcome. Last session of the day. Hope everyone's good. I'm Simon Whiteley. Hello.
I'm Craig Porteous. Hey.
I'm going to talk about how to build a lakehouse on the Microsoft Intelligent Cloud Data Platform thing, which is an interesting mouthful, right? There's a lot of words in there. There's a lot of things in there. So this is a nice, gentle intro session to Synapse, what the components are, if someone's talking about a lakehouse, what a lakehouse is, and how you use the two together. If you're going to build a lakehouse in Synapse, how do you go about it? What's the thought process? How should we be thinking about applying these tools and techniques? That's the plan.
Easy.
Yeah.
So we've got all day, right?
Yeah, we've got, I mean, no one's allowed to leave. The doors are locked. And we're going to talk about this for a while. It's fine. Okay, so we're both from a company called Advancing Analytics. We do consultancy around lakehouses generally. We build a lot of Spark. We build lots of advanced analytical things, hence the name. Also, our logo is a D20, which means we are the most themed for this conference known to man. So it works. We're both Microsoft MVPs. So we spend a lot of time talking to Microsoft about how they're building a product, where the future's going, what they're doing, how things are coming out, why don't things work properly, various different things. But essentially, even looking at what the tools are, how they work, how they fit together, we can give you a fairly good idea. We are also working heavily with Databricks. So we do a lot of Spark. We do lots of work with other competing Spark engines. But again, focus on Synapse for today. Mm-hmm. So, the Microsoft Intelligent Data Platform. What is it? Anyone have a really, really strong idea of what it is? Even the Microsoft folks. So eventually it came out as this idea. It's a unification of all the various different tools and components in the Microsoft ecosystem that can be used to produce a data platform. Everyone clear? No? OK. Essentially, it's a way of just telling the story a bit better. And actually, it bears some resemblance to what was known as, was it, the Cortana Intelligence Suite? Anyone remember that? Yeah. Like umbrella term for lots of these different tools that go together to say, this is how we build things. Now, when we zoom in and we focus and we say we're talking about that middle piece, that analytics, we're talking about how I make a data platform, in reality, we're talking about three things. We're talking a bit about machine learning, we're talking about this Azure Synapse Analytics, and we're talking about Power BI. So we're kind of zooming in, right? We've got this big umbrella term, big marketing fluffy term, and we zoom in and we go, OK, we're actually talking about some specific things. And then if we're talking specifically about this nebulous idea of a lakehouse, we focus in on one thing in particular. So starting off big, broad category, lots of things we could talk about. Zoom in a little bit, zoom in a little bit more, and in reality, we're talking about this thing called Synapse, or Synapse, depending on if you're American.
Synapse?
Synapse?
Yeah.
I got told off by Microsoft calling it Synapse too much. OK, so what is Synapse?
Yeah, so who's familiar with Synapse here? Who uses it? Oh, loads of hands. OK, skip this section. It's fine. Yeah. So Synapse is kind of made up of many different components. It's not just one kind of product on its own. We've got the Azure Synapse Studio, which is the main kind of way you're interacting with these components. Underneath that, we've got the clicker doesn't work. There we go. We've got the orchestration component. So that's your integration pipelines, basically data factory.
I've been slightly naughty there and put the data factory logo. Technically, it is, yeah, Synapse integration pipelines, but it's data factory.
Same thing. We've got our governance layer, Microsoft Purview connectivity in there as well. We also have 5 different compute engines. So on the SQL side, we've got our dedicated SQL pools or SQL data warehouse or various other naming iterations over the years. We've got the serverless component. And then on the Spark side, we've got our Spark engine, and we've got data flows, which actually uses the Spark engine under the hood as well. And then we have, sitting all on its own, is Data Explorer, which is how we can explore or how we can interact with time series data using Custo query language, KQL. So all of that is sitting on top of a data lake. You can't deploy Synapse without a data lake. And to surface it all, we've got Power BI in there as well. We've got the usual kind of management, monitoring components, data sources, and everything as well. So that's Synapse. It's a mash of so many different components. Mash, is that maybe not the right word?
No, mash kind of makes sense.
Yeah.
I mean, the strong message in there, right, is, as you said, you need a lake. You cannot deploy Synapse without having an Azure Data Lake Store Gen 2 resource. And I talk to people and they're saying, well, this Lakehouse thing, how do you know it's the right direction? How do you know that this is what people should be focusing on? It's like literally, this is a lake product. This is a lake product that has some other options in there, but the base foundation of it is actually built on top of a lake. Loads of like that trend in terms of databases and new tools and technologies. They're based on this idea of separate out storage and compute, apply elastic compute to some storage that's in a distributed cloud layer. This is baked into this technology. So we're talking about lake-based processing, which then becomes a lakehouse when we do some certain other things, and we'll get to that.
So yeah, digging into the engines themselves, I'll start with the Spark engine. So that's a scalable cluster. Our Spark engine gives us an executor at the top. It's got workers where we can distribute the jobs that we're running, and we can scale them up. We can add more workers in. We can scale it down when we don't need to. We don't need that capacity, and then back up again. So it's nice and flexible. We can also use a wide selection of languages. We've got Scala, we've got Python in there, SQL, R, and we're going to get the same performance no matter what one we're using. We've got that flexibility. We've also got C# in there, but from Spark 3.3, C# is no longer supported. Basically, it was based on an open source project, and .NET 3.1 went out of support, blah, blah, blah. So C# is no longer an option.
Who was using Spark.NET? Sorry.
One person. Sorry.
We have the one person in the world who is using it. So, I mean, just in terms of scales through executors there, that is 3 words that don't mean a lot unless you are a massive Spark nerd. So just to put, hello. In terms of what we're thinking about, the whole point is distributed. The whole point is parallel. What Spark does under the hood, you give it a query. You say, go and query these files sitting in a lake. It brings back those files as little chunks of data. And maybe if I was querying, I don't know, 4 gig of data, and I brought back, and I had 4 executors. Each of those executors has to process 1 gig of data, and it takes a certain amount of time. And then, if I actually want that to go faster, if I have 8 executors, well, each one only has to do half a gig of data. So it's going to finish faster. So we can scale just by adding more workers. Each worker does a smaller amount of data. We spread it across the entire idea. So it takes data, breaks it into lots of little blocks, little chunks, things called RDDs. It spreads them across workers in a reliable, parallel, distributed way. So when we talk about how many executors do you need, it's, well, how much data do you have, and how fast do you want it to go? You can make it go faster by adding more executors, but that's going to cost more because you're paying per executor. And that's always the decision.
Mm-hmm. Yeah. So moving on from Spark, our Spark engine, coming back to the SQL side of things, we've got our dedicated pools, or SQL Data Warehouse, or what was previously your parallel data warehouse. And that works in a kind of similar way, where we've got that executor, we've got our compute nodes, but you don't really get to see any of that. Essentially, you're looking at a number that is DWUs. DWUs, yes. Your data warehouse units. So that's how you scale your dedicated pools up and down. And you've got a range of, what, 100 to remortgage the house and everything else. Yeah.
But so it's hidden away from you, right? You're doing in these chunks of 100, 500, 1,000, 1,500. Actually, every 500 data warehouse units is another compute node. So if you have 1,000 DWUs, you've got 2 compute nodes. You've got 2 lots of parallelism. If you go to 2,000, you've got 4 lots, and each one does less work, and things go faster because parallelism, it's the same thing. But very much this is based on the SQL engine. So it's a different idea, different way of working, but the idea of parallelism is still there.
Yeah, you're SQL only with that as well, so you're still interacting with a SQL server. So moving on to serverless. So that's based on a new SQL engine, Polaris, which Simon's going to tell us lots more about.
There's a really, really nerdy, deep white paper, the Polaris white paper, which goes into the detail.
People have got time.
Yeah, you guys want to know how it works? I can tell you a little. What it does, it takes data that's stored on disk, it breaks it into small chunks of executable code, it spreads it across a number of workers. Is that sounding familiar? Essentially, it's the same ideas and principles of parallelism that apply in Spark, but it's applied purely to SQL Server. So it brings up these little SQL servers in an idea called a data cell. It gives that a certain number of tasks. It decides how many it needs and how many it doesn't need. So at runtime, when you run the query, it'll just allocate a number of those SQL servers, spread the work out, but that's all black box. So it's doing some really smart stuff. It's doing the same idea of parallelism, distributed query processing, all of that good stuff, but it's doing it invisibly. So you just write a query, hit go, and it will just figure out what to do and return the results, which is nice.
You don't have to worry about it. Startup time with that approach, that cluster, is about 10 seconds if you've not used it for a couple of days, but beyond that, it's instantaneous. Don't need air quotes for that. Is it instantaneous?
It's mostly instantaneous.
Mostly instantaneous. Yeah, so because it is a little bit black box, your performance is a little bit variable, I think, but it's got that flexibility.
Yeah. It's generally, performance is very, very good in serverless. Occasionally, you'll get it hang and it won't appear for a few minutes. That's actually gotten a lot better recently.
Yeah.
But the problem is you can't debug it. If something's happened, you've got no access to it. You're like, so you're trusting the fact that it'll work, and you're trusting the fact it's going to get faster and more performant over time. But black box comes with a price. It comes with a lack of ability to go in and lift the lid and see what's going on inside.
Yeah. OK, which ones to use then? So you have you want to do some ad hoc data exploration, serving via serving to visualization, that sort of thing. So
people writing SQL queries, people doing experimentation, just doing a little bit of data analysis, people serving data into things like Power BI. It's going to be serverless.
Yeah.
All right, back at you. If we're doing framework building, if we're doing some data science, if I've got some libraries in Python, I want to use scikit-learn, I want to do some machine learning and do some real nerdy stuff, or I want to build a data engineering pipeline that's parameterized, what do I use?
Spark.
Always Spark. Always Spark. And then if I want to do something really secure and fixed and reliable and robust with huge, huge data processing scale, it's going to be dedicated.
I was going to say Excel. But
that's the idea, right? There's these different tools that you've got baked in Synapse. They have their different performance. They have their different cost. They have their different use cases. They have their different languages. And that's quite hard, right? You're given this, hey, we've got one tool. It's all in one place. And actually, well, yes, but they're different. You need to understand how it works. You need to understand which one to apply in those different scenarios.
Is
that dying? Well, we'll just do the thing. So absolutely, Spark is fundamental to getting that Lakehouse automation thing working. We tend to do that as a bit of a mix. Now, when we talk Lakehouse, we don't talk that bottom one, because dedicated SQL is not actually a lake. It's a SQL server. It has its own database storage. It stores data baked into it. So we're saying, how do we build a Lakehouse in Synapse? It's a combination of the top two. Now, I've said that word a few times now, right? Lakehouses. What's a lakehouse? So I explain lakehouses a lot. This is how I spend my every day, just ranting at people going, lakehouses are great. Part of it is because I've just been through so much pain in the world of data lakes, and lakehouses have changed how we think about doing things. So let's have a bit of a talk, see if this thing works. So the things that a database is really, really, really good at. Databases are structured. I have a really good fixed schema. I've got good data typing. I've got real performance things I can do inside there. They're governed. I can have an audit trail. I can say, well, you're allowed access to that. You're not allowed access to that. If someone goes in and changes something, I've got a log of it. If someone goes and just accidentally deletes all my data, I can restore a backup. So there's a load of really, really good things inside a database, which is why people have been doing data warehousing in databases for a long, long time. They're also fast for specific things. So they're really fast. I want a specific one single record. Great. I can index the hell out of it and make it super, super fast. Certain queries don't scale that well in a SQL server. And I realize saying that at SQL bits is kind of naughty. But then switching around and looking at a lake, Well, lakes are so flexible. You know, a lake is just network storage. It's a file explorer. I can store audio files, video files, I can store documents, I can store the complex nastiness that is JSON, which shouldn't be that hard. But I can store any kind of data I want in a lake. It's so flexible. It's also cheap. Cloud storage is super cheap. I think the last time I looked, storing data inside a premium storage inside a database is something like 5 times more expensive than storing it in a lake. And because of that, people go, well, I'm going to store more data then. And it scales better. I can't run out of storage space in a lake. I can in a database. So not having to think and go, ooh, have we got enough space to keep 10 years worth of data? No, we can only keep 3 rolling years of history. Those days are gone. We don't do that anymore. You store whatever data that you want. Obviously, there's a cost. The more data you do, the more it charges you, but you don't have to think about that. I'm going to run out of space. You're not constantly looking at that cliff coming close to you going, do we have enough space? So it's scalable because of that. And it's fast for different things. There's a thing in cloud storage where if I put a single file, if I get a big CSV and I put that in a lake, and it's like 2 gigs worth of data in a CSV, which is kind of criminal, but you can. Actually, even though you see it as a single file, if you log into the Azure portal, you see that file, you'll see a single file. Secretly, under the hood, it breaks it into lots of small chunks. It makes 3 copies at least of every one of those chunks, and it keeps them in different combinations. Now, because I can access each one of those chunks in parallel, I can throw massive parallelism even if I've got a single file. So lakes are great for big, chunky analytical queries over huge amounts of data or small amounts of data. But they're built for that kind of thing. They're not so good at saying, I want a single record. So it's different performance characteristics. So what we saw is a load of people kind of just jumping off the bandwagon, joining the hype train and going, I want to move away from a warehouse, I want to build a lake. I'm going to use lakes for everything. And it was, it was really hard. It was a terrible idea. And that's because lakes themselves have gone through this evolution. So lakes used to be, back in the day, text files or CSVs.
The Wild West.
The absolute Wild West. Now that means every time I query the CSV's got no data types. The CSV doesn't have a schema. I have to figure out the schema every time I read the data. And that's really hard. I can give it the wrong information. I can get my data types mixed up. Someone can add a new file into that folder that's got a different structure, and then everything breaks. Doesn't make any sense. So people thought, we're going to get better. We've got a better idea. Started using Parquet. Has anyone ever used a column store index? Cool. Parquet is just that as a file. It is a columnar compression format flat file. Now that's great. It's got a little header and some metadata. It has its own schema. It has great column compression in there. I can select just one column from the file, and it's much more efficient than reading the whole file. Parquet is fantastic. But I've got no audit trail. I've got no governance. I've got no backup. If someone's running a query against some Parquet, and then someone wants to update that Parquet file, they need to delete it and recreate it. And, you know, ACID compliance in a server we all know and love, if my data's not there when I'm trying to query it, it's not going to work. So Parquet had huge problems, but huge gains, but huge problems. And then along comes more modern file formats. So there's a thing called Delta. Delta Lake is a modern file format. It's based on Parquet. So Parquet is still there. Parquet is still the thing. All of your data is still held as Parquet files with that good compression. And Delta wraps a transaction log and some governance and things around the top of it. It is more of a file protocol. It's not a specific file type. You'll still have Parquet files and a little JSON transaction log. But it enables so many things. Now what we can do with that is then evolve in our journey. And that's where Lakehouses come from. Now you could just say, well, Lakehouse isn't a thing then. A Lakehouse is just a data lake where you're using a specific file type. That is all a Lakehouse is. It's not some brand new technology. You'd have to rip all your data out of a lake and put it somewhere else. A Lakehouse is just a lake that is using a better, more modern file protocol, such as Delta. There's also Apache Hudi and Apache Iceberg that do similar things, similar ideas. Because I am a big old Sparky boy, Delta works really well with Spark, and so we tend to use Delta as our default. So actually what we're trying to say, a Lakehouse isn't a shift away from those things. A lakehouse is a bringing together of saying, let's learn all the good things, all the things that were great about building warehouses, all the things that are great about a lake, smash them together. Let's learn from warehousing. And it's really hard, because it means, I'm celebrating when we get things like, we've got column defaults. We've got identity columns now. And everyone in the database world is like, yes, slow clap.
Decades ago.
But that's it. We're learning from databases. And we're learning those things that, yeah, they've been around for years, but you've never been able to do that in a lake. Or to do it in a lake was a massive workaround and a pain. So we're implementing these things to bring things forward. So what can Delta do? Technically, it's an optimized managed format for organizing and working with Parquet. Now, the official Databricks explanation is like some massive, long thing about what it achieves. But that's what it is. It's Parquet, but better. That's literally it. So there's a bit of secret sauce. I'm going to show you how Delta actually works under the hood. So I got something like this. I've got my sales folder, and I've got some Parquet in there. Now, I'll have a transaction log. Now, this log will say, currently, these Parquet files are part of my Delta table. It's like a file manifest. It's a rolling list of which Parquet files are currently part of my table. So whenever I change my data, literally all it's doing is going to add more data in. Now, Parquet still hasn't changed. I still can't edit a Parquet. I can't open up a Parquet file, change the values, and recompress it. It doesn't work like that. So if I try and do something like this, and say, delete star from sales where segment equals 3, if I try and do any kind of data update, it doesn't change those files. It makes a new Parquet file with a new version of the data. So there's lots of data that's been copied across those two. If I read all of those 3 Parquet files together, I would see, well, the old version of the files, the new version of the files, and it just wouldn't make sense. So what that transaction log doing, the new transaction happens. It says, I've added this new Parquet file. Consider this new Parquet file part of my Delta table. No longer consider the other ones. They're now the old state of data. A little bit like how SQL temporal tables are working. And all it just works based on this rolling list, which Parquet files are part of the Delta table at any one time. And that's really cool, because that means I can do temporal querying. So if I say just select star from my table, that'll go in. It'll see the transaction log. It'll realize the first 2 Parquet files are no longer part of my table, and it'll just read the Parquet that it needs. If I do select star from sales before that transaction, where timestamp as of yesterday, well, the removal of those old ones hadn't happened yet. The addition of the new one hasn't happened yet, and it'll read the old version of the table. Simple. And because I've got that transaction log, it's also got who did it, when did they do it? Was Simon drunk at night and wrote a merge statement that deleted all the data? Yes. Roll back the data. Great. We can roll back individual tables rather than having to restore a backup of the whole database, which is pretty cool. So that's Delta. And Delta means we can do this thing called a lakehouse, because we now have structure. There's a central schema held in that Delta transaction log, so I actually have a governed schema that can evolve, which is great. It's governed in that I have an audit trail. I can restore things. I've got all the good backups, the protection that you need to run a professional warehouse. I can write merge statements and delete statements and all those things, which you cannot do unless you're using Delta. Plus, it's still fast and flexible and cheap. So that's all a lakehouse is. Lakehouse is a lake using Delta, using advanced file formats that apply all the good stuff from warehouses, but we get all the scalability and flexibility of a lake.
And it's open source.
And Delta's open sourced. It's out in the world. You can use it in lots of different places.
Yeah.
So, where could you build a lakehouse? So you can use Synapse to build it. You can build lakehouses in other cloud platforms. You can build lakehouses using Databricks. You can build lakehouses using Synapse. You can build lakehouses using lots and lots of different things. It's controversial having a snowflake logo on here. Because they have the thing called Snowpark, and you can do elements of Spark in there. Is it truly a lake house? But you have lots and lots of different approaches. So what we're saying now, this isn't the only way to build a lake house. We're just saying, well, if we wanted to do that, if we wanted to build a lake house and you want to use Synapse to do it, you want to use the Microsoft Intelligent Data Platform to do that, how do you go about doing that? That's the question.
Yeah.
So it'll end up looking something like this. You'll end up saying, OK, I'm getting some data from somewhere. I'm pulling it in to a landing blob. And then picking that up and doing some shaping. Raw-based curated, that's what we tend to call it. You might see it called bronze, silver, gold. You might see it called 1, 2, 3. I don't care what you call the layers of your lake, as long as your users understand why you call it and what it means. If your user understands that they get some data from raw, that's going to be unprocessed. There might be errors, it might have problems in it, it might have duplicates. If your users get to some data from gold or curated, they know it's gone through a data engineering process. They know it's clean, they know it's validated, they know it's good quality data. That's what is important. It doesn't matter if you prefer bronze, silver, gold, or raw-based curated, or whatever you call it. Easy.
Fair.
Okay. So, engineering. Who's a data engineer? Yeah. So, I spent a long time building SSIS packages. It's just like this misspent youth of building lots and lots over and over again. I'd build the same packages, doing the same thing. I'd copy and paste a template. So we had this idea, if I've got a load of different tables to load, every single different thing I loaded needs a different package to go and do it. So if I'm loading 10 tables, I need 10 SSIS packages saying load this data. If I need to add a new table, I need to add a new SSIS package. Or any ETL tool, Alteryx, or whatever it happens to be. I need to write a new SQL stored proc to load that thing. Whatever it's doing, it's very manual, it's very bad. The test cycle is horrendous. Every time I change something, I've got to test everything, I've got to redeploy everything, I've got to make sure it's all right. I have no agility. Now people said, we can get better. There's ways around this. And there's a whole wave of ETL automation tools. So we go, actually, what we're going to do, we're going to get some metadata. We're going to turn a crank that's going to automatically make a load of those tables. Lots of people use Biml. Biml's really, really good for doing that kind of thing. But you still have a load of code objects. Your code footprint is still huge. You still have to deploy those objects once they've been generated. You need to pay fees. You need to learn how to get C# and XMLA and jam them together in a horrible hybrid. It still doesn't really solve the problems by having an automation framework that is building code for you. So what we're trying to do these days is saying, actually, I want to have just a generic process. I want to have a generic script, a single script that doesn't change, and then just pass some configuration into it. And then suddenly, actually, my code doesn't change when I add new data. If I want to add a line of metadata saying add this new table, my code hasn't changed. I don't have to deploy it. You cannot make DevOps go faster than not doing a deployment. So keeping this idea in mind, you can just start to build better things. Now, the flip side, yeah, you've got code complexity. We're no longer using a GUI. We haven't got a user interface to build things. We're writing a bit of code. We're using a programming language. So there is a shift in how we think about things. There's more complexity in terms of how we build these things. But in the grand scheme of things, I'm writing less code. So if I'm saying I want to move some data from bronze to silver, raw to base, whatever we call it, that's one script. And yeah, that one script is slightly more complex than a stored proc I was looking after, but I don't have 100 stored procs to load 100 tables. I've got one script that I then have to manage. So my code footprint is small but complex. It's kind of just word of warning. So you end up with a process like this. We have a thing called a Jupyter notebook, or a Spark notebook. So I've got some PySpark, I've got some script. And then I can call that just from integration pipelines and pass parameters in. So if I say I need to load 10 tables going from bronze to silver, I call the same notebook 10 times in parallel, just going pass parameter table A, parameter for table B, parameter for table C. So I'm parameterizing. I'm having a metadata-driven framework to help load things. Maybe I'm pulling that config from a SQL DB or from some JSON, or I don't care where. I can store some metadata, I can have a generic process, and I use that metadata to drive that process. That's what we can achieve by switching to things like Spark. That's what we're trying to get to. So all my notebooks is doing this. I go, right, okay, read some data in, transform it, write some data down to the next stage. So I build my process out of those generic building blocks. Read some stuff, do some stuff, write some stuff.
Sounds like a familiar process.
Oh, we'll get to that. My invention.
You copyrighted it?
Yeah, absolutely. I don't think it's going to work. So there's a few concepts that we need. So we've got a thing called a data frame in Spark. And that's kind of a weird concept, because you open it up, and it looks like a table variable. It feels like a table variable. It's not. It's a query. And that's confusing. Essentially, Spark is building up a set of instructions. I'm saying, well, read that data, and then filter some data out, and then change the columns. And each time I add instructions, it's just changing the query. It's not running it. It's not getting the data. A select star in Spark is perfectly fine. Oh, everyone is shocked. Because what you can do, select star, and then filter it to what I need, and it'll go back and it'll push that, and it'll change the query. It won't do the full read and then bring things down. It's a bit like query folding in Power Query. So actually, each instruction actually gets turned into a good execution plan by the time you run it. So some of your patterns is slightly different. So I've got some little bits of code examples to talk through. And this is as complex as we really need to do some basic ETL. I'm saying data frame equals, df equals. Again, that's naughty. It's a bit like calling a variable I. Df is just, it's the lazy person's variable name for a data frame. Spark.read, format of Delta, format of JSON, format of CSV, or whatever I'm reading in. And then .load to where I'm pulling it from. That is generic. I can parameterize that. I can say, well, actually, for this one, pass in JSON as the file format, and that's the location. For this one, pass in Parquet as the file format, that's the location. My script doesn't change if I'm chopping and changing which things I'm loading from. I can make a generic ETL process. In terms of doing data transformations, I can say, well, OK, make a new version of my data frame, overwrite it, transform my data frame. With column, I'm going to add a test flag. EXPR is the easiest way to get started in Spark, because what we can do there is write SQL. So I'm saying, add a new column. I can't be bothered learning PySpark, so all I'm going to do is do EXPR, that's an expression. I give it a string that's the same as a SQL column would be in a select statement. So I can write case statements, I can do window functions, I can do most things that you can do. I can do regex, regular expressions to go and replace data, but I can write it as SQL. And I just jam that in as this with column. So we can, again, and because that's a string, that blue bit, that case when, can be parameterized. I can pass that in as a parameter at runtime. So building up, my dataframe.read, or my spark.read, can be parameterized to read different file formats from different locations. My transformations can be parameterized to run different snippets of SQL and apply different transformations. Writing data, shock horror, can be parameterized. Dataframe.write, write it out as delta. This is where to write it to. So I can build a really, really generic script that can read data from anywhere, transform it with anything I pass in, write it out anywhere. So we talk about how ETL changes, how we change our mind about how we build these things, going from the days of each and every table has its own bit of code that I have to manage and look after, to I got a generic process that can do anything. So yes, I need to learn some Spark commands. But actually, you don't need to learn that much, it's not crazy. So my invention is this. So I read some data from somewhere. I'm going to call that extract. I'm going to apply some changes and transform things. I'm going to load it somewhere. Call it ETL. I think it's going to catch on. Yeah? Yeah, there we go. Now I'm going to make millions. But it's the same idea. All we're doing, every single little component, all the notebooks to move data through my entire lake, read some data, transform it a bit, load it somewhere into the next stage, rinse and repeat until you have curated data, facts, and dimensions, and that's it. So yeah, there's effort and work in building those processes up. But it's not different. We haven't fundamentally changed the world. We're still doing ETL in the same way. Lakehouses follow the same process. We've been building warehouses for years. Just our technology changed a little bit. That's it. Change the world.
Simple.
Now, one of the things, one of the secret sauce, which is a little bit different in Synapse if you've used Spark elsewhere, is how we get these parameters in. So I've built my nice generic notebook. How do I get it to run that thing with different parameters? So I just want to show you a couple of examples of what that looks like. So we have this, parameter cells. So when you're in Synapse, you've gotten your notebook with various code, you can grab a cell, and you can tag that and say, make this a parameter cell. Now this is based on an open source approach called Papermill, and all it does, at runtime, it overwrites anything that you've got a variable for with anything you pass it from your integration pipeline. So if I've said table name equals, schema name equals, and then when I call this as a notebook from my pipeline, I go, oh, add parameter table name, add parameter schema name, and if I've supplied those, it simply overwrites those variables. So I can inject variables into it as long as I've got a parameter cell, and as long as in that parameter cell, I'm setting various variables. That's it. That is the secret sauce. So I have my notebook. I say, call this notebook. This is the notebook I want to run. Here's the parameters I want to pass. And actually, I can get that in a big loop. And suddenly, things just, actually, it's not a crazy new thing we need to build. I need to build these basic building blocks and then hook up the parameters to it, which works. Easy. So taking it back, our architecture of things is a bit like that. So we might be using integration pipelines to go and get the data from somewhere and bring it into our landing blob, the same copy data, the same data factory way we've been copying data into Azure for years. When it's there, we've then got a Jupyter notebook that says, read the data in my landing blob, apply some changes, land it into raw. Read the data in raw, clean it, get rid of special characters, tidy my data, all the data cleansing, ETL stuff you guys are experts in anyway. Land it in to my base or my silver, my middle layer, my clean layer. Read the data from my clean layer, apply some transformations, make it dimensions, look up surrogate keys, apply slowly changing dimensions, whatever I'm doing, write it into the gold layer. It's all the same techniques. We break it into these component parts, we write those generic notebooks. And then when we're running it, again, the same as we do any kind of metadata-driven data factory, it's a look up a list of things I need to do it for each, call that notebook passing parameters in. And these are building blocks we've been using in Data Factory for years. You can do all that inside Synapse, and it all kind of sits together, all hangs together, the same as you'd expect. So we've done that. We've been good engineers. We've stitched everything together. Data's moved through our process, and we've got a curated layer. What do we do with it?
Serve it.
Well, there we go.
So this is where serverless comes in. Essentially, when you're using serverless SQL, it's such a familiar process. It's such a familiar interface if you're used to SQL engines. You've still got tables, views. You're writing in SQL as well. It's not really anything that's going to be too alien. You're not talking about significant changes in skill sets as well. So you can even create stored procedures, which aren't exposed through the Synapse Studio, but if you connect through Management Studio or I believe Azure Data Studio as well, you can still see those stored procedures. So you can see them under the hood. But as we mentioned before, you don't need to think about scaling with this. The downside being that it is hard to troubleshoot within serverless, as it's a bit of a black box.
Yeah.
But what about Delta? So we've got those tables in views. How do we see our Delta tables? So again, we're writing this in SQL. We're creating views which point to Delta table locations. So again, it's a familiar language. It's a familiar way to interact with the data. You can also do that with external tables within serverless SQL, but you're going to need a higher level of administration rights to be able to interact with it. And external tables are probably better suited for things like row-level security, if you have requirements for that. Otherwise, stick to views. Some downsides being that you can't do partitioning in views, you can't filter in views as well.
No, so views do partitioning, external tables don't.
The other way around.
Views perform better. Use views, we like views. But yeah, it's a little bit weird getting used to writing open row set every time you're trying to load a table that's there. But once you've saved that view, you can just reuse that view for lots of different things.
Yeah, exactly. And working with views as well, you can add that with statement to your command as well to basically handle data type changes. When you're working with your Delta tables under the hood and you're exposing them as views, all your varchars are going to come out as varchar max or 8,000. So that's a good opportunity to change your data types and update your data types to override.
It'll just keep things faster. It'll keep things cheaper because it's having to do less data movement once it's actually in serverless. So just generally be good with your data typing.
So considerations with Synapse serverless works out about £5 per terabyte read. That's how the charging kind of works. And it will vary depending on the region that you're in, but roughly £5. And In terms of use cases, you're not going to want to use it for intensive workloads and things. As we talked about, performance isn't guaranteed. It's better than it used to be. And what else? What would you say the more benefits of serverless?
I mean, yeah, it's fast and it's really easy and it's familiar.
Yeah.
Whenever someone says, should I have that or should I just use direct query over serverless? It's like, no, please God, no. And there are some scenarios, like if you are hitting it constantly, costs are going to rack up because it's pay per query read. So sometimes maybe moving all that data and putting it into somewhere else, if you're going to be doing massive rereads of the same data, there are some cost considerations for that. But generally, if you're doing like an overnight refresh of a Power BI report, hell yeah, serverless is super fast, super easy. If you have to go back to the lake and do real-time queries, it can get a little bit awkward. Now, the one thing I do need to say with serverless, whilst you can, do not write data using serverless. You can do a create external table as select. You can, in serverless, go read some data and then write it down. You have no control over the files and the performance and the delta and partitioning and all the stuff that makes a good performant lake, all the stuff that makes it a lakehouse. You can't do if you're using serverless as a quick hack to write data. So just because you can, doesn't mean you should. So that's why we use Spark. Spark, we've got control. We can make sure it's really good and really fast for the users who want to query the data, and they do it using serverless. OK, so if we're saying it's not great for direct query, how do we do it? How do we think about getting data from our delta table, from our gold layer, from our nice facts and dimensions, and getting that into something like Power BI where people can actually go and query it? I mean, absolutely. If your query fits into import mode, just do it. It's nice. No problems there. Great. Hit it when you need it. No problems. Direct query has some interesting challenges. The same with hitting direct query on anything. So how do we think about doing that? Well, firstly, if you don't use Power BI that much, direct query tends to run a query per visual. So if I've got a big dashboard with lots of different pieces on there, each one of those is going to run a query. So if someone goes into my report and hits refresh, and it goes and gets those numbers, it's not going to run one query and charge me one bit of data read. It's going to run lots of different queries, all in parallel, and charge me for each one. So you need to think about how you're structuring your report, how many different things are, maybe have some high-level dashboards and then drill down to the details and not try and build a dashboard which has every single KPI and hits every single thing, because it's going to throw a lot of stuff back to serverless. And that might have some performance problems. It might have some cost problems. Now, generally, and I'm not a Power BI person, warning, not a Power BI person, how do we go about thinking of having a data model but keeping the cost down if we're using direct query? If we have to use direct query, essentially it's a data modeling problem. So you can say, well, actually we'll do a composite model. We'll do some of the dimensions we're going to keep actually on import mode, and it's only the big chunky fact table, only the big deep one that's too big to fit in the model. We're going to make that direct query. But then even that is going to throw a lot of data back down, so actually maybe we can use aggregations. So we can apply aggregations as a small amount of data is kept in the cache, it's kept in the import model, and only if they drill down to the lower level details, it's going to use direct query. Or even more, we've got in the future, we've got these hybrid tables of actually that rolling, the most recent data is kept in, and all the data you've got back. You've got different data modeling approaches that you can use to try and make sure maybe 80% of the users coming in are hitting the import thing, and that's not going to go and run serverless. And only when they need to, it goes and uses direct query. They're the kind of patterns that we have. Again, not a Power BI expert. There's plenty here. Go ask them. But just think about the data sets. Think about the model that you're using in Power BI to try and think how often we have to go back to the lake. Because it's going to cost you each time you go back to the lake, because that's how serverless works. So just think about it. Design your data model with that in mind. And then, yeah, essentially, that's how we build a Lakehouse in Synapse. We have integration pipelines using some metadata, running lots of these Spark notebooks, passing parameters into the Spark notebooks to automate the process of moving data through our lake, getting the data to a point when it's nice and curated, and then serving that out through Synapse. So serverless. That's the bits and pieces that we stick together. The one extra piece of the puzzle, so Purview. So Purview is a governance tool. It's not officially part of Synapse, but it's part of the Microsoft Intelligence Data Platform. goes in, keeps an eye on the tables. And that can be baked into Synapse. So people querying via serverless can come in and go, customers, and get a list of all the different tables that have things to do with customers. If you've got your data well cataloged, it's a great place for people to serve and explore and go and investigate data, provided you've actually done the process and got the data in there and got it all working together. All right.
You're going to get your lineage as well through your integration pipelines.
And you have your lineage.
Coming from and how it goes through.
And even into Power BI, which is nice. Cool. That is everything